Hello. All right. So everyone's here who I think is going to make it today. Welcome to the meeting. We have someone new here today, Paras Mahan. He was recommended by Ujwal and Asmit, and he's going to work with them on the digital basilaria. Paras, could you introduce yourself?
Hello everyone, I'm Paras Mahan. I'm second year BTech undergrad at IIIT Delhi, and I like. Is everyone able to hear me?
Yes.
Yes.
So I like digital. I'm into machine learning a bit stuff, and I see the project is very interesting, and I'd like to work on it. That's it.
Okay. You have a background in machine learning, you said in your email. What kinds of projects have you done in the past few years, or what's your background in that area?
I've actually worked on an autonomous car project in my college, so it involves a kind of a digital visual stuff, and I've also done a couple of mocks, massive open source courses. That's it.
Okay. Sounds good. Well, welcome to the group, and you'll see our group meetings. We talk about two projects. We're talking about Vinays GSOC project, which is image processing and machine learning, and then we'll also talk about digital basilaria, which is the thing that you're working on. And then we also do things like we present papers and we do other types of activities. So why don't you just sit back and enjoy today, and then if you want to maybe present a paper or something, we can talk about it later. So okay, good. Does that sound good?
Good. Thank you.
All right. So what we're gonna do today is we'll why don't we have Vinay start? He has a presentation for us on his paper, Super SloMo, which is actually, I think it's this will be interesting to the digital basilaria group as well, because it's about motion processing. Am I right?
Yeah. It includes a bit about motion processing and also related to optical flow. It will definitely be related to that.
Okay. So why don't we get started? Can you share your screen?
Okay, yeah. So we'll do the boards later.
Yeah, we'll do that afterwards.
Okay. So I'm starting right now. Just give me a second.
Yeah. All right.
Can everyone see my screen now?
I can.
Yeah, thanks. So today I'm going to be presenting a paper called Super Slow Motion. Actually, this paper is published in CVPR 2018. CVPR is like the most prestigious and biggest conference for computer vision and pattern recognition related tasks. So this has been presented by NVIDIA. The research has been done by NVIDIA team and also people from some universities. And these are the people who have written this paper. And if I can go to next slide, yeah. So this is basically the contents that I'll be discussing now. Firstly, I'll be talking about the aim of the paper, like what problem is it solving, what is the input, what is the output, and basically I'll give a slight overview, like a skimming experience of the paper, and I like to discuss what are the previous works that are existing for solving this problem, like what are the drawbacks for that, why is the need for a research on this problem, and then I'll be explaining the approach, like what they have discussed in the in the paper itself. And they have dedicated a separate section for training the model, and I'll be discussing about that too. They have used some uh, custom loss functions for that, and I'll be posting some images and pictures regarding the results. They've conducted many experiments, and they've been to they've done an analysis of how the model is performing compared to other previous existing models. And of course, the most important thing, where else can we apply this? Like, how will this be useful? That section will be doing this. So let's jump into the aim of this thing. So the aim is to actually first, if you can see the demo for a few minutes. So this is the original video, and this is the video that the model has outputted. Like this is a slow-mo. This is a slow-mo version of this one. Here, this is a 60 frames per second video. The deep learning model has converted that to a 480 frames per second video model. And these are some other experiments that they've. So I think basically you get the idea of what this paper does, what this research does. So when we have whenever we want to do some super slow motion videos, we need some special hardware for that. This research eliminates the need for special hardware. What we can do is that we can take a standard videos, like already recorded videos, and if we can input that video into this model, this this model can split the frames, split the video into frames, and can generate some intermediate frames between the original frames. Like everyone knows, the video is nothing but a collection of frames with nothing but images. So how can we increase the number of frames in that video? If we can increase the number of frames in that video, then automatically we can view the video in slow motion. So basically, that's the idea of this. In the paper, they discussed the input and output pipeline like this. Like if two input images are given, the model should be able to generate a multiple number of intermediate frames between those two input images. I think we can understand this better visually. So I'm skipping this. I'll be attaching some photos for that. Before that, I want to discuss about the previous existing work on this problem. There is some work. There has been some research that has been put into this problem, but most of them are only for single frame interpolation. That means that between two frames of a video, we can generate only one intermediate frame. So most of the previous approaches are focused on that, but this approach, like what the paper discusses, we can generate any number of frames between any two between the successive frames of the original video. And there are actually a few methods which are capable of multi-frame interpolation, but they are like very expensive computationally. They involve deep mathematics and higher level integrations. So that's kind of a drawback for that. And we can there's also possibility that we might think that as this single frame interpolation exists, so why can't we recursively run that? Like if we input the original video, if we can do the single frame interpolation on that, we'll get a slower video. And if we can plug that again to the model, it will get a slower video. And if we keep repeating the process, we'll get a much slower video. We can do that, but there are some limitations for that, which inspired these researchers to pursue research in this. So the problems for recursively applying this into a single frame interpolation is that the errors keep accumulating as you keep going down the process. Like as you keep repeating the process, uh, you'll be having many distortions in the images that are generated, that are synthesized. And also a parallel computation is not possible because if you'll have to wait for the frames from the previous step before you go to the next step to generate more images. And most of the existing models, when there are objects moving in the video between two frames, most of the existing models, they are suffering from some occlusions and motion boundaries. Like the motion boundaries get faded away, slightly faded away, or they get stuck at a point. All these I will be showing all these things like visually. And there's one paper that I think needs a special mention. Wang et al. Tried to generate intermediate frames from a light field video. Like this paper, this SloMo paper is actually an unsupervised way. It is built in an unsupervised way because there are no labels, or there is nothing that the model has except for the input video. So what Wang and people did is that they've captured a process with a normal camera and a high frame rate camera, and they tried to build a model which can learn from that high frame rate camera, but that also did not go well. So we arrive at this paper now. So the approach of the paper is that they basically have two convolutional neural networks, both of them having a unit architecture, uh, and one. So basically, there are three steps in this. The first step is that they'll use one CNN to estimate the bidirectional optical flow. I'll be explaining about what bidirectional optical flow is in the next coming slides. So when we are given two input images, the first CNN then can compute the bidirectional optical flow between the two images. And they needed an another CNN because the computation of bidirectional optical flow is not that level of good, and they wanted to refine those results and also take care of occluded objects, or or the objects which are blurred, or any kinds of distortions basically. So that is the second step. um, from this second CNN, we will be getting some visibility maps. If we apply those visibility maps to the output of this first CNN, then we'll be getting a final input. The final output. So those are the base, the key steps in this approach. So let's get into each step at a time. So for suppose this is how it looks. If we have an image, like if we have two input images, like this is at 0th second and this is at 1st second. So the model tries to generate an intermediate image here, which is between this and this. So how does it do that is the main thing here. And yeah, it must be able to generate an image like this at a time t equals some value of t between 0 and 1. So I have discussed about the first CNN, right? That it will be computing the bidirectional optical flow between two input images. What is that bidirectional optical flow? It's nothing but it's this image. Uh, For each pixel of this image, it will be calculating the corresponding corresponding value of the pixel in those two input images. Like actually the flow is defined as in a way that for a pixel in an image, as the video as the video keeps on going, there will be a vector. For suppose in this image there's a pixel here. Now after some time the pixel moved somewhere here, so the flow of that pixel will be a vector pointing from this direction to this direction, from here to here, like that. For each and every pixel there will be some flow. So when the video keeps on moving, like keeps on going, all these pixels will be moving to a new place, or some pixels will be added and some pixels will be removed, like that. So uh, so the first CNN calculates that accurately. And the reason why they call it bidirectional is that because it takes, for suppose this is a pixel, it takes the flow difference between the corresponding pixel of this input image and that input image. That's why it's called bidirectional flow computation. So that the first CNN actually does that. And why is that useful? I'll be telling you. So let's get into some mathematics behind it, like the basic thing, like how this is working. If we think, if we can denote f of t from 0, t flow from t to 0, like from this image to this image, and f t to 1 from this image to this image, like the flow from this image to this image. So this is the formula for getting the output image, like this intermediate image. After applying this formula, we'll be getting this image. And here G, they have defined G as a warping function, which is basically used for fitting this thing, fitting the input images, and linearly fusing them, so that there won't be much difference from the input images. We'll be explaining about that warping function also. And they've also introduced a new variable called alpha. So the intuition behind alpha is that, for suppose it controls the contribution of the two input images into the intermediate image. For suppose I want to predict an image at times that t is equal to 0.1 second, then by common sense we can say that all those pixels from t equal to 0.1 second will be from this image, like from t is equal to 0. If we want to predict from 0.9 at time step t is equal to 0.9, then most of the pixels will be contributing from this image. So alpha takes care of that intuition. And are there any doubts that I want to say? Ujjwal, I want to address that at the end. Can I do that?
Yes. Let's save everything to the end.
Yeah. Thanks. So I'll be continuing the presentation. So we come. So we got the output from first CNN. Now we need to apply some visibility maps so that this output is defined and we can make sure that it's not blurry or it's not repeated or any kind. So basically this visibility is defined like in a way that v of from t to 0 of p, that means for each pixel there will be a probability. For suppose if I for a pixel p, this function defines the probability which lies between 0 to 1 and it denotes whether the pixel is occluded or not. Like the model tries to predict a pixel in the current image, will that be occluded in the next image or not? So a complete zero tells us that the model is predicting that the pixel will be occluded, and that cannot be contributing to the computation of intermediate image. So that is how the visibility maps are created, and this is the function that they have defined here. This is some deep mathematics, to be honest. And I forgot to tell about this. This is nothing but a element-wise multiplication between two. These are all matrices. All of these terms, all of these input images, flow images, visibility maps are all of the same size of the input image itself. So they will be using element-wise multiplications to get the output image. So here at this step, we'll be getting the final output. So this is the mathematics behind that, and let me get into some visuality. Yeah, the main basic thing is that in the first image, I told that we'll be taking bidirectional flow components from this intermediate image to the both of the input images. But how do we get this intermediate image is the question. Like once we get an intermediate image, we can keep on refining that in the training process. But how do we actually settle at an initial intermediate image? Basically, because we did not know, like we don't know what the image will look like at t equals to some small t. So for that, uh, they wanted to depend on the flow from t of 0 to t of 1, and they calculated uh, the flow of image from t to 1 like this. And also it's also conversely true for this also. And this is how the formula that they have defined for getting the flow from t to 0 and t to 1. And so this is the pipeline of the model. These are the two convolution neural networks that I spoke. This is a U-shaped architecture here. And first we will be getting the input images. We will be pushing the input to images into the convolution neural network. It will compute this based on the first two images. We'll get this value and also this value. Based on this value, which is the flow from 0th image to first image, we'll be getting this value. And likewise for this. So we'll be getting the flow value from tth image to 0th image, and also the tth image to first image. This is what the convolution neural network here mainly does. So after the input images pass through this, we'll be getting bidirectional flow for the two input images, and then here the visibility maps come into play. Here after applying this formula on the input image and sending it to this convolution neural network, we'll be getting a refined flow and also the visibility maps. They combine these two to get the actual output prediction. And also all the parameters that are included in these images, in these models, are time independent. So we can generate any number of intermediate frames that we want in between these two images, in between the input images. So this is the illustration that they have given. I think all these things starts making sense now. These are the two input images, and they're predicting intermediate image. This is the image at 0th second, and this is the image at first second. And they took small t as 0.5, which is so the model has to predict an intermediate image at 0.5 second. So this is how the optical flow has been derived from the first convolution, and these warped input images are nothing but the application of this formula here. This is the backward popping function. This is a combination of these two which produces these two images, and after that uh, we'll be sending them into the second convolution neural network, which will be providing us the visibility maps here. Like whenever there is a motion between two input images, then we'll be having the visibility maps highlighted like this. Like that indicates motion, and the neural network learns to not to get too blurry over there or not get any distractions over there, and that's all. And the model gets all that from the training process. So let's get into each of these images in a bit detailed way. So these are the two input images. This is I0 and this is I1, and we took an intermediate second at 0.5, and this is the flow from 0.5 second image to this zeroth image, and this is the flow from 0.5 second to image at the first second. So these are the outputs from the first convolution neural network that we will get, and after that, and also these warping also happens in the first convolution neural network itself. So if you're not able to understand the term warp is nothing but it's like distorting an image into a shape that we need. So that's basically a definition of warping. And this is the visibility maps that you can see here. And they've applied these visibility maps to the intermediate flow images, and they've gotten the results like this. Here you can see the output of the first convolution network, output of the second convolution network without any visibility, with visibility maps, without visibility maps. So here you can see there are some boundaries highlighted here because of the motion. The player is moving his hands like that, so the motion got stuck over there in the intermediate image. But after applying these visibility maps, we can see that the neural network got to understand that these should not be stuck over there and this should be moved like this. So it will adjust the pixel flow in such a way that the loss will be minimum. I'll be discussing about the losses also. And yeah, this is how they train the model. So the final loss function is a combination of four losses. This is the reconstruction loss, this is a perceptual loss, this is the warping loss, and this is the smoothing loss. So I'll explain I'll explain the purpose of each of this loss now. Like this loss function, this is the reconstruction loss function. It explains how good is the reconstruction, like how close is it to the input images. This one governs that. And perceptual loss. This loss is used to avoid having blurry images, because we might end up having blurry images even with visibility maps. So when we are applying the second convolution neural network, this loss function helps us to get rid of blurry images and other distractions. And there's also a warping loss function they are using to compute the loss. It's actually it's basically to model the quality of the optical flow which is computed in the first convolution neural network. And there's a smoothing loss that they've added. It is to encourage the neighboring pixels to have similar flow values. Like if the neighboring pixels of a moving object are also having similar values, like similar movements, then there'll be less chance of having distortions in the reconstructed intermediate image between two original input images. And these are the results from the experiments that they have conducted. Here you can see the two input images, and this is the actual ground truth. Like the actual intermediate image is this, and these images are all the outputs of the of previous existing methods, and this is the output of the current research paper. So here you can see none of these papers have visibility has the concept of visibility maps. So sometimes when the brush is in motion, it tends to get blurry when the reconstructed image is formed, and sometimes it gets shaped out like this, of a small movement of shaping out. But in this paper, the results produced by this paper are pretty accurate like this. They've given an example comparing all the outputs of the previous models. And regarding the training process, it tends to outdo all the approaches at each time step of the video. Like, there are some approaches which come close, but by far this is the best now in terms of constructing super slow motion videos. So basically, trying to give a small recap of that. These are the key points in the paper. So they use two unit architectures with nothing but convolution neural networks, and one does compute the bidirectional optical flow between the two input images, and the other unit is used to refine the approximated flow. Like, the flow that we get from the first images is refined, and the visibility maps are generated. These visibility maps are combined with the output of the first convolution neural network, and then basically we get the output. So the data that they've used is that they've used about 1132 240 frames per second videos for this data. This is an unsupervised approach, so there are no requirements for any labels for this thing. All these loss functions take care of getting good results. And where can we apply this? It has a lot of fun and also interesting applications. Like, suppose if we have a video which is very fast and we can't afford a camera to capture it, so we can take a video of that process with our normal camera, and if we can plug that into this model, this will produce a super slow motion version of that original video. And for suppose if you want to generate data from a video like we did for spin images, like we can generate more intermediate frames between those original frames of the video. So that is an application. And also we can pay keen attention to the process that is happening in a video if we want to, if that's a requirement for us. So yeah, we reached the end of the slides. I think we have some questions. This is the thank you slide. So I'll be answering the questions. 1 second.
Okay, very nice. So we had one question from Ujwal from in the middle of the talk. He said FT. It's basically that FT is a linear interpolation. So
actually, yeah. Like the FT F from T to 0 is basically nothing but the flow from teeth image to the zeroth image, like zeroth time step image. So so it's kind of a linear interpolation to my understanding of this, because when it's not only linear, actually it can be maybe polynomial also, because we can generate so many intermediate images between that. So if we want to generate so many intermediate images between just two input images, then I think this flow computation will have some polynomial functions to solve, so that it will get a vector from the initial point of a pixel to the final destination point of a pixel. I hope that made sense.
Yeah. Yeah, I guess I had a question about that too. So, I mean, if you had a very simple type of motion in the image, like you had like a motorcycle moving against a background at a constant speed, that would be like you could probably use a linear interpolation for that. But if it were like a very complex form of motion locally, like a chemical flow, where you had high amount of mixing between things, and you could actually see a lot of different types of different velocities and different things like that within the same image, then that would be. I wonder if it would basically fall apart on something like that, or if it could handle.
Yeah, the basic understanding that I would get from this paper is that I am suspicious about how well it would work for change of intensities across across the video. Like for a pixel, if the intensity doesn't change, that won't be much problem to track that pixel. If the intensity is changing too much, or if it's moving too much, I think that's a problem. But even if it's a video of a liquid mixing here and there, so there's no big difference, but only the displacement vector changes. For suppose for a motorcycle video, if we take the motorcycle going from left to right, the pixels from left to will have a flow vector from left to right, right?
Yeah.
And if we take the if you take the video that you said, like chemical flow, chemical liquid flowing here and there, then we will have we'll have the flow vectors scattered across the image, like it will be in different directions. Maybe that will be computationally a bit expensive to get to make sense of that, and input that to the second convolution neural network. But I think it would also work well for that.
Yeah. Well, they have like super high rate cameras now where you can sample at like a million frames per second, and they're expensive. But if you were in a situation where you wanted to like, I mean, could you train it on something that sampled at a higher rate? So you'd have basically the same video, but you sample it at a lower rate, you sample it at a higher rate, and then compare the two. The lower rate capture with this application, and then compare it to the higher rate video and see what the comparison is. Because it seems
Sorry, I did not get the right question correctly. Can you repeat that?
So I guess if you like, so they have cameras that have like a super high sampling rate, like a million frames per second.
Yes, yes, yeah,
It's
yeah.
like they're industrial applications, scientific applications. But if you took that camera and you captured something, and then you captured the same thing with a camera that say had a lower sampling rate, and then you use this method to predict motion or resample
Okay, okay. Yeah,
frames.
I get it. I
Yeah,
get it. You're asking how the output of this model will be compared to the original output from a high frame rate camera, right?
yeah, yeah,
So yeah, we know that although how good the deep learning is, it's only as good as the data. So if we provide more and more data, maybe there will be a time and technology where it can reach that level of accuracy. And as of now, I think like all the videos that I've seen regarding this paper, uh, all the articles that I've read about this paper, they suggest that it gives some satisfactory results. But the drawback that they mention is that sometimes it gets too smooth, like it gets blurry when it's extremely fast. When there's object moving extremely fast, and if you try to use this method, and so they've observed that it gets a bit blurry, that movement of that object. Yeah,
yeah. It's like
but
Nyquist theorem. So you run up against this aliasing effect where you don't have enough data to kind of tease out everything, and it sort of
yeah,
averages.
exactly.
Yeah. Okay. Well, very good. Any other questions for Vinay? I know this is something that the people in Digital Bachelor have been talking about, at least, or thinking about. Vinay's been thinking about it too in his project. So, um,
Yeah, also, I think we need to be some conscious about the mathematics behind it, because in the paper they have discussed some high level mathematics, some which might be intimidating for us. Like it's not like intimidating, but it might take us some time to implement it, or better, there actually the good thing is that there are some already implemented. Some people already implemented this thing and they posted on GitHub, so maybe we can take that and try to understand the code, put the code and the paper side by side and see what they're doing like that.
Yeah,
Maybe that will be useful to
yeah,
understand, to get past that high mathematics, or not being afraid of that high mathematics.
yeah. Well, I mean, just implementing mathematics and code is always a challenge too. So
Yes,
having
yes.
it. Okay, so Ujjwal had a question. I think this paper focuses on continuation of the frames in camera, which has a very high resolution, works on capturing more and more number of frames. So in quick videos, it becomes blurry because of loss of items in RGB space.
Yeah, exactly,
Yeah,
Joel. I was like I had this in mind. Uh, I don't know how to express that. I wanted to get an example, but kind of tangled up my thoughts. But yeah, that explains. I think that explains Bradley's question, previous question.
yeah. Well, yeah. If you have any other questions for Vinay, you can ask them in Slack. So, and then next week we're going to have Esmet present his
Hmm.
paper, and we'll. I'm sure it'll be interesting. I can't remember what it is right now, but so let's move to the boards. We have about 20 minutes left. Let's see. So the first board we'll do is Vinay's board, GSOC 19. Let's see if I can get the chat here. I'll post it in the chat. Here's the repo. And if you go to that link and you go to the repo and you go to the projects tab and you go to the DevoWorm Summer of Code project, here's the board. And now we're gonna review again. We'll just review in progress and to do this time. So in progress we have set up use deep learning for J, number 8.
Yeah, like last week I mentioned about a limitation for deep learning J, right?
Yeah,
So about using some custom layers inside DL4J. So I've also slacked you something like I got past that error. So what happened this week is that after getting past that error, I fell into another error which seemed like a dead end to me. So after trying to figure it out myself, there's actually community for deep learning for J. So I went there and I've explained my code. I've I've implemented the toy problem to reproduce that error, and I posted that. So they said that there's no current workaround for that for my case. So probably that is something I have to discuss with you.
okay. Well, what is the so is
Yeah,
this
yeah.
like a dead end or is this like something that you think you I mean, what is the actual problem?
Yeah, I can explain that. Initially, it seemed like a didn't. Like what I've actually did is that in my Python model, like the deep learning model which I implemented in Python, I used a custom convolution layer, which is like the heart of that model, which gave the output that I've shown last week. So in their documentation they mentioned that lambda layers are possible. So like these lambda layers, what they do is that whenever we implement a custom layer, it'll wrap this lambda layer can be used to wrap around that, and this custom layer will also be treated as an inbuilt layer for Keras. Basically, Keras has some inbuilt layers like convolution layer, or recurrent neural network layer, or LSTM layer, like that, right?
Yeah.
So whenever we have to implement some custom layers and wrap it with, and if we wrap it with lambda layer, then that behaves like an inbuilt layer. So in their documentation, they mentioned that it is possible, so I went ahead with that method. But in their examples, they mentioned only simple computations uh, like square root computations or addition computations. But in my case, I had some convolutional computation also in my custom layer. So I put that in their channel, and they've said that they don't currently support that. So basically that's kind of a limitation for me right now for that.
Hmm. So are you thinking about solutions to it, or are you like, do you think you can work around it, basically?
Yeah, I have a few ideas for that. Basically, now I have it in a, I have the whole model in Keras. So I implemented the custom layer in TensorFlow. Like I needed some low level computations for that. So I went for TensorFlow. So I'll try if I can convert this Keras model into a TensorFlow model, and then import that TensorFlow model into deep learning for J, because they have a pretty good pipeline for the TensorFlow model.
Okay.
So that is one option that I have now, and the other option is to change my implementation itself, because I need to remove that custom layer and try to play with the parameters that come with the inbuilt layers of Keras, and basically try to see if I can get any results from that. Those are the two options that I can see for the next week.
Okay. So yeah, well, why don't you try those and keep me up posted on Slack about your success with that. Um,
Yeah, definitely.
okay, so that's all right. So that's that. Then I made a new issue here, implemented custom layer in Keras from TensorFlow number 23. We'll put that in progress, and then we can talk about that next week.
Yes,
Implement
sure.
unsupervised approach. So I think that's what we're talking about with phase one. So you
Yes, yes.
submitted a pull request for your phase one code, and so I accepted that right before the meeting. So that's in progress. Maybe that's done. Number 10, and we can revisit that. You said you were going to revisit it after you finished phases 2 and 3. So
Yes, yes.
conclusion of plugin development scheduling. This is the phase, yeah, the revisitation. So I'll leave that in progress.
Yeah.
Data augmentation strategies number 20.
Yeah, data augmentation strategies. I've discussed with you that I've also uploaded the code for that about last week. Like there's a list of data augmentation things I've considered. Like I did the resizing of images. I did shifting, left shift, right shift, up shift, down shift, and histogram equalization. So basically, I applied all the basic data augmentation things, and then I've trained the model.
Okay.
So I think that strategies, there's no issue with that strategies.
Okay, so you want to put that in done?
Yeah, yeah,
All right,
yes.
we'll put it in done. Okay, work on paper presentation. You did that. Build a plugin Java number 13.
Yeah, basically I have the plugin ready, plugin code ready for that. So I'm waiting for this deep learning code to get done. If I can get that done, I can just copy paste it into this plugin code. I also uploaded the plugin code into the template plugin code into the GSOC main repository. You can go through that once. So I'm just waiting for this deep learning issue to get resolved. Once I get it resolved, I can just copy paste that dependencies and code into this plugin code. So once I'm done with that, I think the entire thing will be done. The phase one will be done for that.
All right.
It's kind of a linked issue with limitation for deep learning for J.
Okay. Yeah. Okay, so then limitation of deep learning for J, we can also put in progress, and then we'll kind of link 13 and 21 together. All right. Then in to do, begin work on semi-supervised approach. That sounds like you're going to start that within the next week or two, so we'll leave that in the to do. The DevoWorm and neuroinformatics outreach.
Yeah, actually, I posted about a conference, right?
Yeah.
In Slack. Actually, I thought of applying that, but after I got, I had some. I also have mentioned that I had some issues with my RAM and all. So, and also this deep learning issue. So I thought of not going for that because I may not manage time
Okay,
for
that's
that.
fine. Yeah.
So probably I can do such a thing. So all these conferences will year long, right? So I can go search for a conference where I can speak about my project once I get some free time. At present, I think I'm into this issues.
Yeah. Actually, I was talking to Ujwal too about outreach, and he had a different conference in mind or a different group. So we might talk about that, like between the three of us. I'll put it on later. Uh, there might be something there that we can all kind of do together. Well, we'll see. But I'll put a note in here about that.
Yeah, and today I bought a RAM and I got fitted it today.
Oh, good,
So
good,
that's basically in that for this week.
good. Um,
Yeah.
and then okay, and then we have two more here. Implement Softcut normalization loss.
That's kind of implemented, but I not find any much use for that. So I just kept that in the repo, but I don't use it anywhere.
Okay, and then segmenting bright field images. I think that's in phase 2 or 3. So we'll come back to
Phase
that.
three, yeah.
Yeah. So any other issues that you want to create before we leave the board?
So sorry.
Okay.
Only that, yeah. Only the limitation thing. If I can get past the limitation thing, and then I think I'll be able to. Uh, I'll be able to complete. I'll get done with this unsupervised approach, and also for the semi-supervised approach, it will be much faster. Like once I get this pipeline thing done, it will basically be the same thing to do for the semi-supervised approach also. Like, of course, the implementation for deep learning model in Python will be different, but importing that deep learning model into this Java application will be the same. So this is like the main issue for me right now. If I can get this right, the subsequent phases also, this is like a repetition task for me.
Okay. That sounds good.
Yeah.
Okay. And so that's good. Now let's turn to Ujwal and Asmit and Paras. We're gonna go to the digital Basel area board. So let me put the link to the repo in the chat once again. And if you follow that link, it'll bring you to the repo, and we'll go to the projects tab. And then the projects, we will click on the board there. There's one link. Digital Basel area. And here's our board. And we'll just go through the Inprogress and to do issues again. Let's start with Inprogress. Number 17, adding information about biology of Basilaria. I did a little bit of that this week. That's an ongoing thing. Model evaluation. Are we coming on that?
For this week, we have actually because we are following a kind of transfer learning approach because deep lab is basically a like uh, pre-trained model on a really large data set. So we actually just work on the last layer of that the model. So for that we need some amount of label data. So this week we actually started labeling our frames. So I guess it's the second video, one of the videos. We started picking random the images which are far on the timeline of the video to have a variety, and we have I have posted around 10 labeled images in Pascal work format, that's .xml files. So we'll actually need these XML files to train our model. So like this is the ongoing thing like for this week and maybe the next week also. The three of us can work on it and maybe get 100 to 200 images labeled by the next week. So once these are labeled, we can feed them to our model, the deep lab V3 model, and we can see the results after that.
Okay. So yeah.
And we are able to see the results.
Okay.
We have a plan like we are going to label around 100 to 200 as Shweta said, labeled data, which is like a detailed level data of every filament in basin area, and we will feed them and we have the results for that.
Okay.
Uh, I have created a new repo, not a new repo, a new folder named labeled images, and then I have the XML files and an image folder which contains the images for which the XML files are there.
So okay. So then, what do we want to create any issues for that, or I mean,
I guess like we can create labeling data set for them.
all right. And then we'll just do add, and let's see what we can assign to this. So number 35, we created that. I'll assign all of you to that, all three of you. And then that's just, I'll put a short description. We want 100 to 200 images labeled for training. Okay. And there you go, update. And we'll actually put that in progress since it sounds like you're going to do that this week, or this coming week. So we'll put that there. Now, model evaluation, it sounded like there was like, that was linked to some other things, so we'll leave that aside for now. Schedule and present papers, so Ujwal presented, and Asmit will present next week, so we'll put that in done for now. Alright, and then mathematical model development, number 27.
So so because obviously the model may not perform perfectly. Like if we have total of 20 filaments in one image in one frame, so if we can detect around 10 in one, 10 in the other, like overall, like there will be different kinds of segmented or like images will get the output will be different amounts of cells for a different frame. So it's not possible that we can simply map these rectangles movement by simply like just after getting our segmented images that will track the movement of the rectangle. So what we have to do is like I guess we like between the frames we actually need to do some kind of Kalman filtering, which is basically like a function which takes in account like all of the frames and all of the movement in the future frames and past frames, and like makes prediction accordingly that there should be a filament or a particular rectangle here. So we have to use some kind of algorithm like this, and once we are done with this, then I guess the main task would be to get as close rectangles to the filament in the frame, and then we can map their movement, like the pixel wise coordinate movement across the frames to get velocity and everything.
So in a nutshell, we can say like we are going to label our data and get the results from Deep Lab, which is an unsupervised approach to detect cells in all the frames of the video which we have gathered. And after that, for development of mathematical models, we can use Kalman filters and all these things to get exact location of the cells, and then we can just put the points as you have already included in readme.md of digital basileia. Like we can put the points, and according to their movement we can find what is the velocity and all other parameters of digital basileia.
Okay. So then the mathematical model development will kind of delay that. I mean, we'll keep that in progress, but it'll come after the stuff that we're doing now with the training or the labeling and the training of the data sets. Am I understanding that correctly?
Yeah.
Okay, so that's good.
So actually, Vinay has posted some health-related issues. If you can read.
Okay, what kind of issues do we want to put up?
Vinay has posted on chat something.
Oh, Vinay, or what? What do we? Okay, yeah, Vinay, you can leave. Yeah, we're done for. You're done for today. So, thanks for attending and thanks for giving a good talk. All right. Okay. So what was the what are the issues that you wanted to put up on the?
So actually, as the Richard sir has said, like we have to start documenting our approaches as well. So we have started that, and I will send the mail to you and as well as Richard sir about what we have documented till now.
Okay.
So I think we can put that issue as well in progress.
Okay. What was the documentation of what kind of procedure? Like the
Documentation of procedure what we have done till now.
okay. I'll just a generic. Okay, we'll do that. Let me make an issue, convert to issue. Yeah, I'm going to assign it to all of you. And then, okay. And we'll put that in, I guess, in progress. Then what else? What other issues do you want to put up?
So I think that's enough. Like we have a good amount of tasks for the next week already planned.
Okay.
So
All right. So yeah,
this is our
you have that. Then the Kaggle kernels. I don't know what that referred to, but I think that was like something that you were going to try, but it wasn't like something that's doesn't seem to be central to what we're doing. Uh, welcome to Paras again. And one of the things we do here at Paras is we give, everyone at the beginning, they did a presentation based on their GSOC proposal. So everyone here at least applied to a GSOC project and they presented their proposal to the group. You didn't do a GSOC proposal, so that doesn't make any sense. But what you could do is what Asman, Ujwal, and Vinay have done is pick a paper that like a paper from, I guess in your case it would be machine learning, literature, like in from archive or somewhere from a conference, and do a presentation like what we saw today from Vinay. Kind of review something that really interests you, some approach, or some current issue that you're interested in, and just present on that.
Okay, I'll look at it.
Okay, it's like a 20-minute presentation. So, just let me know if there's something you want to do, and we can set you up.
Okay, thank you.
Okay. Number 31 is description of neural networks approach for biologists. I'm not sure what that was. I think that was something that we did last week. We were going to write up because there was this paper that we want to start writing, but the thing is we just need to write up like a description of some of the methods. So that's actually linked to documentation, I think. So we can actually link 31 and 36 together. All right. And then the review Sabuku et al. That's the paper that I just got that paper yesterday. So he sent it to me, so I can share it with you guys, like on Slack. And as long as you keep it confidential, I don't think you're going to have too much of a. I don't think you're going to be sharing it with other scientists. I mean, just just look at it on Slack, and it'll be. I'll private message you the paper. And it might help with the 31 and 36. So and we'll put that in progress as well. Template methods, again, that's kind of linked to that. We'll put that in progress. And then model features within and between frames. That's sort of related to the mathematical modeling. Actually, I might move mathematical model development back into to do so that we don't, we have enough stuff going on that we don't want to have something in there we don't know what it is or are not doing right now. And then I think the last one is create video resources, and that's something there. Actually, I did get a email from Thomas Harbich, and he actually had in his email, and if you look at the README in the repo, you'll see there's a link to a lot of the stuff he's done with the diatoms. So this isn't just like the basilaria. This is like all diatoms. And he's done a lot of really excellent videography of them and different sorts of things like that. So it's really something, you might want to check out in your spare time. Okay, any other questions you have for me before we go?
No, so from my side,
Okay. All right. Well, it sounds like you guys are kind of in the middle of your like the actual like meat and potatoes of putting together the analysis. So I think you're doing a good job. If you please update me whenever you have something to show. I mean, it's always good to kind of touch base on that and see where you are. But yeah, you guys are doing a good job. Thanks for attending. Thanks for keeping up the good work. And Slack me on Slack if you have any questions. And we'll talk next week. We'll hear from Asmet with his paper. And have a good week.